Good morning, depending on where you may be joining us from today. I'd like to thank you for joining our second in a series of informational webinars that Mazer Consulting is proud to host. I am CJ Ruch. I am a senior project specialist at Mazer. My specialty, of course, is working with scan data. Today, I'm joined by Kevin Hanna, who's our static scanning discipline leader. Kevin, go ahead and say hi.
Hello, everybody. Hope you're listening to us all nice and clearly.
Also joined today by Maria Thorpe, who's our event moderator. So we're here today to talk a little bit about 3D scan to BIM and the benefits thereof. Today we're going to discuss a lot of different things, but specifically the benefits of static scanning versus conventional methods. We're going to talk about some specialized deliverables from collected scan data, BIM basics, LOD or level of development, what that means, and we're going to go through an example. We're also going to talk about Autodesk Revit as the premier BIM software and challenges as they relate to BIM and Revit. Before we get too deep, we're going to go over a couple of key terms that you're probably going to hear me mention a bunch, and Kevin mentioned a bunch throughout this presentation. So the first one we're going to talk about is a point cloud. Point cloud's a group of measured points with coordinate and potentially other values obtained with the laser scanner. The points, of course, represent the surface of scanned objects. Scanning works via line of sight, so objects hidden behind other objects will not be picked up. We can't see through walls. We can't see inside concrete with a laser scanner. It's not an X-ray device. So the next term is BIM. It's actually an acronym. It stands for Building Information Modeling. So various 3D models can be created under this BIM discipline. And those models can have intelligence and metadata to all the working parts within them based on client and project needs. The next acronym we're going to go over is level of development, sometimes colloquially called level of detail. They're not quite interchangeable, but we'll get into that a little bit later. Basically, it relates to how intelligent or detailed a model can be. The final term is one of my favorites. It speaks to how things are in the real world, and that term is spatial relevance. So when we discuss things like spatial relevance, we're really talking about how objects exist and how they relate to each other in the real three-dimensional environment, not in the theoretical design environment, how we would wish to have them perfectly plumb and 90 degrees to each other and all angles being in real whole numbers. Of course, we know in the real world that doesn't happen. Kevin, you brought up a term before that I really enjoyed, preserving reality. And I think that's another way to describe spatial relevance. We are scanning, we're modeling things, and we're creating a model that preserves reality.
That's true. That's a good way to describe it, CJ.
So, Kev, this is where you're going to take over on why we should use laser scanning.
Well, cost is at the basis of so many things nowadays. So you want something done rapidly, quicker, faster, and safer. So beauty of the scanning is, I always use the old analogy where back in the days, I say, if a measurement scientist, a surveyor was to go and gather information, it'd be items A through D, and those items would be gathered in the field. And then if E through Z was required, that would require a further mobilization. But with laser scanning, you're getting A through Z anyway at the time you're scanning, because everything that's within view of the scanner is gathered. So there's no return visits and potential upsets to the objects or the site or wherever you're actually working. So great value, you're getting everything in one mobilization. There's the option to gather photography if needs be. The information's gathered very rapidly, and in a lot of civil applications we can work in complete darkness, like in streets, runways, and so forth. Okay, so a little bit about equipment. It's definitely worth mentioning that just like tools in your toolbox, there's many scanners for many different applications, and some scanners can gather a lot of data quite rapidly and very accurately. Other scanners may be a little bit slower, but the workflow in the field is a lot quicker. So you can see some images there of some typical equipment. Obviously, deploying multiple scanners on projects, you'll gather the information 2, 3, or even 4 times as quickly. Okay, so the scan data, would you like me to keep talking about this, CJ?
Yeah, Kev, this was also going to be your slide. I mean, I can chime in with some of it too.
Okay, so as CJ mentioned at the start of the presentation, laser scanning is based on line of sight. You would be forgiven for thinking sometime if you look at the quote unquote the point cloud that the scanner can see through walls. That's understandable. But the way the scanner works is you set the scanner up in front of the subject matter to gather the information, and then you would move the scanner to different locations to surround it, just as if you were taking photographs. So because everything that we scan is measurable, we can see here on the right of the slide, there's architectural deliverables are very frequent with laser scanning. Architects early on saw the advantages of laser scanning and documenting the real world, particularly with generating BIM and Revit models. Survey deliverables, topographic survey, because again, the analogy to scanning like a digital picture, every pixel is its own coordinate. So there's an XYZ. So survey deliverables like contour maps, topographic surveys, elevations and sections, used very, very frequently, are where laser scanning is applied. And again, engineering deliverables too. It's worth mentioning too that with certain deliverables, particularly survey and engineering, the accuracies are very important because of the design potential. So in that case, the equipment that we use, our workflows, our redundancy checks are very, very important so that we meet or exceed the client's expected accuracy. And on the right there, you can see a typical Revit model derived from that environment there, which is a mechanical room. So just to buttress the comment there, laser scanning now is ubiquitous. Early on, people didn't know what it was. It was quite prohibitively expensive. Now everybody is using some derivative of laser scanning, whether it's the point cloud data or a Revit model or a Civil 3D model.
Well put, Kev. I would say that the 3D models are also rapidly becoming the deliverable of choice. And, there's many, many different formats that they can get these models given to them in too. So with that, I'm going to take over again. We're going to talk about modeling, different things we can do with modeling, how it works. Basically, modeling is fitting simpler objects to the point cloud and using those simple objects and combining them in certain ways to mimic or approximate more complex physical objects when we're modeling directly from the point cloud. So speaking to that, the concept of spatial relevance before, in this way, by fitting objects to the cloud, steel and piping is placed as it is in the real world, spatially relevant. Again, sort of that capturing that reality and preserving it. Models, of course, like any other digital document, are measurable, they're modifiable. They're basically a digital recreation of the entire site, depending on what you want to take out of that site. So with that, models can be a living and breathing document for building management down the line, the basis of refits, as you can see in the image above and below to the right. For instance, you could use these models to figure out what kind of components you can fit within these steel structures, fit around these steel structures. Can I link these components together? The image below is the same sort of idea, but with piping. You can route utilities around that, figure out what's where, and they can definitely be kept up to date as your project progresses. So a more specialized version of modeling off of the point cloud is mesh modeling. So mesh modeling is very useful for a variety of applications. I would say some of the more understandable applications would be to use meshes to create surfaces that would go into Civil 3D, or use them as metadata go into a surface in Civil 3D. One of the more important applications of using a mesh in a surfacing fashion is for doing volumes. The image to the right and below is a stockpile, I believe, contaminated soil. And as you can imagine, if we scan that and have millions and millions of data points on that, we can create a really, really granular volume surface to really precisely determine how much material is in that stockpile. Another benefit of using scanning on something like a contaminated stockpile is I don't have to get near it with the scanner. So another form of mesh modeling would be for very detailed surfaces. As you see in the images above, These are detailed building facades, and you can create irregular meshes, excuse me, and accurately portray those very ornate building portions. So the meat and potatoes of why we're all here today is BIM, or Building Information Modeling. And you'll forgive me if I choose to say BIM instead of Building Information Modeling moving forward, because it's kind of a mouthful. But BIM as the concept is known today is it's a relatively new field. But BIM as a concept in terms of its inception's really kind of been around since the 1970s. The modern incarnation as we know it, when we think of a BIM model, we might think of an image like something to the right. That modern incarnation really was a product of the early 2000s, when processors for computers became better, random access memory became cheaper, digital storage devices became a lot cheaper, video processing, everything became a lot better. So the applications to do things like BIM modeling and other kinds of modeling came a long way in the early 2000s, moving up till today. And we'll get into some examples of some of the cool stuff you can do that require a lot of processing power and everything later. A great resource for everything we're going to talk about today is a site called BIM Forum. The address is www.bimforum.agc.org. The mission for them and other sort of organizations like them is to develop clarity and standardizations of terms that we use when referencing BIM. And they really work with other members of the AEC community. Specifically, BIM Forum works with the American Institute of Architects, Precast Concrete Institute, many others to develop these standards.
There's a lot of good information on there too. It's worth mentioning, CJ.
I would say that the documents are fantastic. They're definitely a little bit dry, but there's a lot of there's a deep dive in a lot of the information that we're going to talk about today too. So, and they also have iterative versions of their document. I think the most up-to-date version is 2019, but they also have the older versions of those documents, so you can kind of see how everything's evolved a little bit. But that's a little bit about BIM. Let's talk about the benefits of BIM. BIM, as we now know, is a more specialized form of modeling, building information modeling, specifically buildings. Some of the benefits you can see in that graphic to the right, but really allows for more efficient planning, design, management of buildings and their systems. Your MEP components, your process mechanical, your architectural components are represented in your BIM model with varying degrees of intelligence. And I keep using this term, but let's define it. Intelligence is going to refer to how detailed an individual modeled object is within your BIM model and how interconnected with other building systems that model is, that individual modeled object. We'll go over that a little bit later, but for instance, if you have a modeled object that is a light, that light can be connected to an electrical system, which could be in turn connected to devices that regulate that electrical system. So every object in the building is interconnected, and BIM can simulate that. One of the best benefits is that systems and fitment of objects can be simulated before construction, allowing for identification of conflicts. And one of my favorites is you can develop instantaneous quantity of your modeled objects and the spaces within your model. There's a little back end work to define spaces, but for items like lease spaces, it's very important to be able to do this, and it can be done instantaneously. So level of development, this is that term I was talking about. I defined it earlier. I've been throwing it around a little bit here. Let's talk a little bit more about this because there's a lot of confusion in the industry about LOD, or level of development. Specifies the amount of development of your model, or sort of in common vernacular, the amount of detail of the model. Remember I said they're not quite interchangeable. You can kind of think of details, well, how close does a modeled object really come to looking like it does in real life? Whereas development, you might lose a little bit of that detail, but what it gains is interconnectedness to other systems. So one of the examples I like to use is a wastewater pump. And for instance, a detail might refer to the fact that if we model that pump and the flanges all have the bolts and we've modeled that visually, it's very detailed. Development might speak more to how that pump is connected into an electrical system, how it might have an overflow that's connected into a drainage system, and that Revit would take account of those things and all that metadata in its intelligence to have those work together. So how well does the individual component work within its system and other systems? How much metadata is there? There's 5 main levels of LOD from 100 to 500. There's an LOD 300, which kind of occupies a hybrid space between 300 and 400. It's generally considered a more detailed or more developed level 300 model with valid equipment connections within your BIM software. For existing conditions, as builting, realistically, you want to stay at that model completion level of LOD 300 or lower. The reason being is that you as a measurement professional, you as a person going in there to scan and to model something, you're not going to have access to the connection points that are hidden. You're not going to be an expert on structural components and everything like that. So you'd really want to model them visually, how they look in the field, but not necessarily with that interconnectedness unless you can guarantee that you know what you're doing there. You want to really speak to your standard of care in that case. Most importantly, it's not a linear effort scale for LOD levels. So if I were to model something at level 200 and it costs X, it wouldn't necessarily be 2X of a cost to model it at 300. It'd be more exponential, not quite exponential, but it would be more of a scalar factor between the LOD levels. So I promised you an example of level of development, LOD, because I think that's going to help you, instead of throwing a bunch of definitions up here like I originally had, I think this is going to help really drive the point home about what LOD is. What does it mean? So LOD 100 might specify a number of, let me back up for a second. Our example is going to be light fixtures here. LOD 100 might specify the number of light fixtures per square footage on a floor. It might simply be a model with a floor, with walls, with windows, and an annotation that just says, hey, there must be, 1 light fixture per 50 square feet or whatever would be required. LOD 200, which is the next level up, is going to give you generic sizes of all those light fixtures that might be on a floor in a certain location. So for instance, every single type of light fixture, whether it's metal halide, a wall pack, fluorescent light fixtures, etc., would be shown in their approximate locations and size, but they might be shown by the same modeled symbol. When we get to LOD 300, which is easy to do with laser scanning, the types of those lights are differentiated and they're shown in their exact location. So for instance, a metal halide light and a metal halide light might be shown in your BIM model as specifically looking like a metal halide light versus a fluorescent light would be shown looking exactly like a fluorescent light. And of course, their specific sizes, locations, orientations are all shown in your model. When you get to LOD 350, now you're specifying exact actual model numbers and makes and manufacturers of your light fixtures and their locations. Level 400, it's the same as level 350, plus you're prescribing mounting and special details. If there might be decorative options, if there's certain angles that the reflector in the light needs to be. LOD 500 is the same as above, but field verified. So it's entirely possible to have an overall model of LOD 300, but have certain systems within that model. For instance, the HVAC, for instance, your electrical system be to an LOD 500 level. Of course, that would have to be specified and caveated, but it's entirely possible. Generally, when you order a model that is LOD 350 or 400, though, understand that it's understood that everything in the model would be to that level of development, 350 or 400, whatever it is, unless specifically specified. So, as I like to say, realize that your LOD level applies to everything in a building, from sprinkler heads to structural steel. So, we're going to talk about Autodesk Revit as the premier BIM platform, and I apologize right now. The township is chipping trees in front of my house as I'm giving this presentation. I am sorry. So let's talk about Autodesk Revit as a BIM platform. Revit is an extremely powerful BIM tool in wide use in the AEC industry. Works really well with other Autodesk platforms, as you expect it might, because it is an Autodesk platform, such as Autodesk Inventor and AutoCAD point cloud visualizations in Revit are done via Autodesk Recap. Floor plans, sections, details, 3D views, images, etc., can be created nearly effortlessly based on the model. So in the images to the right there, we have the modeled image or the model view on the left, and on the right we have the section view. So we can take and create section views wherever we want. We can specify the depth of those section views, and they will generate instantly. Across that model, you could probably do a section view every 16th of an inch if you wanted. I doubt that's practical, but you could, in theory, do that. What's really great about Revit as a platform is that items within the model, if they are removed or if items are added, and they would normally appear in that section view, like that section view would encompass that item, the floor plan would encompass that item, it updates automatically as the model is modified. So you lose very little time revising items. So more about Autodesk Revit as a BIM platform. Many manufacturers are offering families and details for use in Revit. There's a lot of free online resources to find those families, including BIM Smith and BIM Object, which are two of my favorites. So for instance, Pella doors and, GE light fixtures and Lithonia light fixtures make their own families, realizing that, Revit's becoming a very important part of the design process. And they will allow these families to be hosted and downloaded for free, either on their own websites or other places where you can find them, such as BIM Smith.
CJ, this is Kevin again. Could you just spend a minute or half a minute there on a simple explanation of what a family is, and maybe equate it to an AutoCAD block for our listeners that are new
yes,
to Revit?
Of course. So a family in Revit, because I don't think I actually defined that term, family is sort of like an individual modeled object. So for instance, if you look at the video that's playing to the right, that window that we just passed is a family. These individual pumps could be a family. And now families, the doors could be families, the lighting could be individual families. So family is like an individual modeled object. Family can be created by anyone. You can create your own families in Revit. They can be parametric, meaning they update based on other factors within your model, or they can be placeholders too that represent an object three-dimensionally visually. So like I said, these families, having a source of these families is extraordinarily important, whether or not you're going to make your own or you can find them for free. I mean, obviously, the inkling from me would be to search for an existing family that I could use in my models before I try to recreate the wheel, as it were. With Revit, some of the sort of added value here, I think, is with rendered 3D walkthroughs of your site. It kind of gives clients, real picture of what the site looks like. What can we fit here? What's it going to look like when we're done? Everything. And I think that's sort of an added value there. So, as good as Revit is, and as much as I love the software, there's definitely challenges, just like every other software. And some of those challenges I've listed here. It's sometimes difficult to work with state plane coordinate systems. The scale factor for point clouds coming into Revit is sometimes not correct. Revit likes to place objects as planar and plumb and perfect, as they say, when modeling in place in Revit. It's not necessarily what we find in the real world. So this makes modeling some of those systems natively in Revit a little bit challenging. The examples there would be steel and conduit. You got an example image to the right. There's like nearly 4,000 pieces of steel in that model, and I'm pretty sure not a single one of them was planar or plumb. So how do we overcome those challenges? 3D scan to BIM. That's what we're trying to talk about here today. So by using this scan to BIM process, we can place objects with that real good spatial relevance, with preserving that reality that we want to preserve, so we know that anything we add to the site's going to fit, right? We're also using scanning. It's really easy to get the detail that I need to create these models in place if I need to. So you can imagine in the image to the right and above, those pumps, to manually measure those in and to manually measure the components of the pumps to create that model would be very difficult. Whereas with scanning, pretty sure the guys could knock that out in a day, and then I can take this into the office. We can model it in place in very high detail and very accurately. So to get around those little issues that might exist with Revit, using a scan to BIM workflow, we're modeling stuff in upstream applications, and then we're bringing it into Revit. So there are applications that model this stuff that's not quite plumb and everything much quicker, much more efficiently, and then we bring that into Revit to get around those issues. And basically, overall, a scan to BIM workflow is definitely a faster, more comprehensive, and cost-effective way to model your sites and get great results. So that concludes the informational portion of the webinar. We're going to open it up to a question and answer session right now. Before we do so, I'd like to say if you'd like to learn more, or we could take a little bit of a deeper dive, you could email us at surveywebinars@mazerconsulting.com. And if you like what you saw here today, this is the second in a series of many of these webinars that we'll be putting on throughout the next month or so. So check back on Mazer's LinkedIn page to find out when future webinars are going to happen. And with that, if there's any question and answers we can go over, I'd love to do that now.
Hi, CJ. Thank you very much. And thank you, Kevin, as well. I have a few questions from the attendees. The first one is from John. And his question was, do you recommend building families or buying resources?
So many of these families you can obtain for free. I mean, there's a potential to actually, scan items or talk to other firms or whatever who specialize in building these families. I would recommend first, look at those free resources online. So go to the manufacturer. If I'm looking for a specific fluorescent light, I might go to the light manufacturer and see if they have that free right there. Next, I would probably go to some of the other online resources, BIM, Smith, and look for those families there. You can search these various resources for type of modeled object, by the manufacturer, everything. It's very, very powerful. And then after that, you can create these Revit families yourself. Revit, to model things in place, is actually quite powerful as well. It has a lot of different options for making complex shapes than you would think. So you can do that as I would say as a final resort, because it's usually more efficient to find the family you need from a manufacturer from a free online resource.
Okay, thank you. Another question comes from Sean. He's participating from Texas. He asked, how can I validate the concept to bring scanned data into a conceptual design of a Revit model?
So I spoke to that a little bit earlier when I was talking about recap, and we didn't go into too much detail with that. So the way you would visualize scan data in Revit is by using recap. Recap is a standalone visualization tool for scan data, developed specifically by Autodesk and developed specifically, I believe, for Revit and Civil 3D. But what you would do is you would link your scan data, your completed scanned point cloud, from your recap file into your Revit model, and making sure, using various methodologies to make sure that it's placed correctly. And what you can do is you can validate your model by cutting sections through it, by cutting floor plans and setting depths and using limit boxes and everything like that to make sure that the modeled objects are placed as they were at the scan. Alternately, there are options to do clash detection in Revit and other applications that Autodesk owns, which can tell you fairly reasonably if the model matches the scan data or vice versa.
Okay, thank you. Kevin, maybe this is a question that you want to answer. Jen from Atlanta was questioning, she has a potential project I guess in Atlanta and with the utility company. And would you send crews from your New Jersey office?
No, we have quite a variety of skills throughout our network in Mazer Consulting. So we would look at the closest geographic location or Mazer office to deploy our crews. The benefits are that our staff, and we place great emphasis on staff being multidisciplined in all the equipment, in this case, use of the particular laser scanner for particular applications. So they would be deployed from the closest office area.
Okay, that answers that. Thank you. Okay, another question from William. He asked, does Mazer have a library of Revit families for architectural and structural items?
Yes, I would. We have developed that. We've had developed a library of stuff that we've created in house, both parametric and non-parametric. And a lot of these things, as I said before, are obtainable online for free. And we have started a library to sort of index these things, so we have them in house. You know, once you've found the perfect. I use an example of a roll-up door because for whatever reason, it's hard to find the perfect one when I need it. So whenever you have that perfect one, you want to save those families, and especially the families that you've created, you of course want to index them and save them and make sure that you can reuse those in the future.
Okay, looks like we have one more. This is a question from Christopher on data analytics and BIM interconnectivity, as shown on the earlier slide of topography of landfill. And he asked, how does this work in real time?
So to extract the volumes and the topography in the real world from the scanning, once again, this is usually done with an upstream product. For instance, everyone's using Leica Cyclone a lot of times to make meshes. There's other products out there. So generally, in order to get that volume, to get that surface data, you're going to need to make the surface from the scan. It's not like you can simply take the scan and measure a volume underneath it. You would have to develop a mesh for that first a lot of times. I believe that's the workflow in Cyclone still. So you would develop a mesh based on your point cloud, and then you could, from that mesh, you can get the volume data that you need. You could additionally bring that mesh into Civil 3D and others and get the create a surface in there to get your various data from that mesh. Now, it's not automatic, as I said. You have to kind of go in there and do it. There's not really an automated process that I'm aware of right now. I mean, I'm sure we're working on developing that too. As far as getting that stuff into a BIM model, you can reference these surfaces and create these surfaces in Revit itself too. So that can be a part of your model. However, it needs to be developed and placed into that model.
Okay. Looks like we actually have another question that just came in. It looks like it's kind of two questions here. It's from Richard in New Jersey, and he asks, how do you handle a space that is typically occupied? Can you work around the occupants? Do you come in at night? And then second part is, have we done as-built for a client verifying a new construction versus an design BIM model?
So Kev, if you want to handle that, because you're definitely the expert on that.
So the number one thing there is there's a practical element to what we do, and that's safety. So if it's safer for us to do our scanning when there's less people there, whether it's night or in between shifts, we will always do that. And after safety, what we want to do is at all costs to avoid any disruption to the area we're scanning. If it's an industrial plant or in a civil application, if it's a busy intersection, we'll always pick the safest and the option that creates the least upset to the environment we're working in. And regarding verifying a conceptual design, yes, we can do that. If I understand your question correctly, if a concept has been built in Revit and they want to validate or to prove that, provided we're in the same coordinate system, big word there, we can take the scanned information, the point cloud that CJ talked about early on, and drop it into the conceptual model and just visually look at it and see if there's conflicts or issues, which is to get back to the point that I made, it's a cost-efficient way of proving or disproving a design prior to going to the field and finding out that, oh, there's a wall in the way, or this doesn't work, or this doesn't fit. So that's another benefit of scanning without doing any modeling whatsoever, just taking the scan and inserting it into the software that your model exists in this case, Revit.
I'm going to add to that too, Kev. There is definitely applications out there that will help you with this. I mentioned clash detection before. It's sort of one way to do it. It's not foolproof. It really requires a lot of babysitting, for lack of a better term. And as far as, like working around, Kevin mentioned the safety aspects of, hey, if we can go scan stuff at night and, get around any kind of dangerous aspects and, say there's a busy site, for instance, and we have to scan it in the day. For instance, some of the sites that we do in New York City, you can actually scan things with all the cars, with all the people there, and the point cloud can be cleaned up after the fact. There's various ways that we do that to give you a more clean data set if that's what you choose.
Okay, thank you. That concludes the questions that I have here for you. Thank you so much.
No, thank everybody for joining us today. And as I said before, if you like what we're doing here, there's going to be several more of these webinars coming up. So check back to Mazer Consulting's LinkedIn page frequently to see if there's anything else that might pique your interest. And we'd love to have you join us again. Thank you.